Hello class, this is a continuation of the Pigeonhole Principle. In the previous video we saw the Pigeonhole Principle, the general outline of it. And we saw it applied in two different examples. In these examples, I kind of hinted to you that you should first figure out what are the positions and what are the objects in the scenario, and apply the Pigeonhole Principle where there must always be at least one more object than there are positions available. Now, in this last one, this was a rather difficult one. I hope you had enough time to try and solve this. So, here we go. A 2 centimeter square has 9 dots randomly drawn in it. Show that a triangle of area of 1 centimeter square or less can be found among the 9 dots. So I've drawn it here. Here's my 2 by 2 centimeter square. So that's 2, and this is 2. And the area of this is going to be 4 centimeter square. Now, before we continue, I want you to take a look at a interesting principle here. Since this is a square with 4 centimeter square area, any triangle we draw on the inside of this, so let's say we draw this, no matter what triangle we draw, this triangle has to be less than the area of the total square that it is contained in. It's impossible for this triangle to have an area greater than the area of the whole square it's inside of. That's pretty much what I'm trying to get at. Likewise, if we were to take a look at the area of this smaller square here, okay, the area of this, well, that's 1 centimeter, and that's 1 centimeter. The area of this is going to be 1 centimeter squared. Now, for a triangle to be guaranteed to have an area of 1 centimeter square or less, 3 dots have to be inside of this square. Because just like I showed you before, a triangle drawn inside of a square, its area of the triangle has to be less than the area of the square it's drawn inside of. But now, is this guaranteed? Is it guaranteed that 3 dots are inside one inside one of these smaller squares? Let's simulate this using the Pigeonhole Principle. Here are my 9 dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's give ourselves the least. Oh, actually no, before we continue, so remember, we can guarantee, so a triangle of area 1 centimeter squared or less is guaranteed, guaranteed if 3 dots are drawn, or you can say fall, 3 dots fall into a 1 by 1 centimeter square. Let's give ourselves now the worst possible scenario. So here's my first dot. Let's randomly place it in one of these. Here's my second dot. Let's randomly place it somewhere here. And we don't want, let's try to give ourselves the worst possible chance, and let's try our best not to fill 3 dots in this square. So that's 2. Let's try to put 1 here. That's 3. There's 4. Here's 5. Here's 6. Here's 7. Now take a look. Here's my 8th dot. If I'm trying to give myself the worst possible chance of not filling in this square with 3 dots. But now if I try and fill this one here, well, these 3 dots will give me a triangle of 1 centimeter square or less. So let's try and avoid that, and let's put it into the same square here. And I'll take a look. There are no other places for this last dot to go. No matter where we put this dot, it will make a triangle inside a square of 1 centimeter square or less. So no matter where it goes, it will guarantee to be a triangle made of area 1 centimeter squared or less. So a triangle of area 1 centimeter squared or less, I'm reading from here, is guaranteed if 3 dots fall into a 1 by 1 centimeter square. By the pigeonhole principle, we can say 3 dots must fall into one of the 4 1 by 1 centimeter squares, since there are more objects than positions available. And there we go. So that's the pigeonhole principle applied in a rather abstract way. So I hope that gave you an insight into the pigeonhole principle a little bit more. And yeah, hope to see you in the next video. Best of luck.